to try to see which hydrogen atom was lost. Okay, so what they did was that, as I said, they were shooting electrons, different energies here, that's this scale here, and looking for the signal of accelerating this fragmentation part. And then they made a trick. They replaced one hydrogen by a deuterium, and then they looked at this channel again, losing a hydrogen atom, not a deuterium. And then they could identify that indeed it was this one which was lost, which was seen because you excite the vibrations in this bond at these specific energies here, which were identified by calculations. So this is an article from this year on the isolated biomolecule without any.
So in the second plot, it's destroyed then.
Yeah, this is the signal of this destroyed molecule.
Yeah, right. Because the little figures are missing there on the left.
This is the signal from the part from the molecule without one hydrogen atom.
And it's these two figures where you have the dotted lines in the upper plot. Right?
That's the vibrational resonances for that.
Right.
Okay, so the conclusion from this was, well, as I said, already known before, but the sub-eV electrons were able to destroy this or to at least damage this molecule, and now it was also identified which specific bond that was broken. Okay, so this is a beautiful experiment. I mean, this clearly, but still, I mean, there are a lot of some criticism from about this method in general, and that is, people are saying that from biology, I think, what is the significance of doing such experiments, because the molecule will behave differently when it's in solution than it does when it's free.
Question. I mean, you broke the ANH bond with an energy below 1 eV.
Yes.
The bond itself should be stronger than 1 eV.
Right.
So how did you do that?
Well, I mean, the molecule was of course not in its ground state from the beginning.
Okay.
So I mean that makes it possible. Yeah.
You get energy from the electron affinity.
That too, yes.
You bind the electron with some
Yeah, okay. So that goes
like an associated.
Yeah. Okay, and what one should do then, according to this criticism, would be to do the experiments instead in a more realistic situation. And this is what we have been trying to do. And how does astrobiology enter into all this? I don't know quite, but maybe there is a connection here. Because if you think about biomolecules or molecules in space in general, I mean, is it possible that they stay together, or I mean, do they need protection from other molecules? And if so, if they need protection, how many molecules are needed? Do we need one big snowball, or is it sufficient with a small number of molecules? So this would be then lead to studies of radiation damage of single biomolecules in nanodroplets of water and other solids. And two people working with this are recognized here. I don't know, Henrik, how you managed to make this picture.
It's inclined, yeah, and you put it back up again.
Yeah. All right. So then we had to select a molecule, and what we did select was this so-called ANP molecule, which is a part of this DNA molecule. It's a nucleotide. So the name is adenosine 5-monophosphate, and it consists of adenine, a sugar molecule, and a phosphate group. So there are several representations of this molecule. All right. So, again, this is the part we are looking at. This is a part of the DNA. So it would be interesting to see how this is damaged when we transfer energy to the system. The experimental technique, sort of the heart of the experimental technique is this electrospray ion source. And it consists of a small needle in which you have a solution containing the substance you're interested in. And then you put a high voltage between this one and this plate here, and you get droplets out, and they are in general charged. And of course then, when they come out here, I mean, they evaporate some solvent molecules, and when they get sufficiently small, the charge makes it fission when you reach the Rayleigh limit for this droplet. But it can't hold any more charge from the size. It will fragment into smaller droplets. So you get charged, in this case, nanodroplets containing one or several AMP molecules, or possibly something else also. So how do we deal with that? Well, what we do is very conventional. We have an electrospray ion source here. We accelerate it to accelerate ions by 50 kilovolts. And we have a huge magnet by which we select the M over Q of the beam. So we have this distribution of different mass to charge ratios from the products coming out from the electrospray. By setting this field to a specific value, we can select one of these masses by this slit here. We run this beam through a collision cell that may contain either neon or sodium. And this is mainly now a way to transfer energy into the system, or to exchange also charge. One should remember here that the flight time from this cell now, with this energy of 50 keV, while if it's singly charged, would be 5 to 10 microseconds. So what the results I'm looking here is what survives this flight time. So at the end of this system, there's a hemispherical electrostatic analyzer. That analyzer is sensitive to the energy per charge, because if you set a field here, a specific value of the energy per charge, of what is left here in the beam, will hit this detector here. And if you change the voltage here, you will select another E over Q, and therefore another fragment. Because the molecule is coming here, okay, and then something might happen here, such that it loses a part. Then the mass changes, and the energy also changes, of course. And if the charge is the same still, you will need to set this to a different value than you would have to if you were looking at the incident beam. So the way to look at the mass spectrum is to change the voltage of this reflector.
But the beam is then not sharp in that horizontal direction, because you have all the different EOLs, even in a single beam along the width.
This is a single beam, and when you go into here, of course, it lights up in different trajectories.
Yeah.
But different, sharp trajectories, because
They were sharp, yes.
Okay, so now these are the two first spectra I show here. So now I'm looking at the output from this, measured by this detector here, as a function of the voltage across these two, and this is converted into a mass per charge scale here. And we have done two different sets of experiments. In one set we have collided with a neon target, and you see here this is the intact molecule. We do it like this, that we have a fairly thin target of neon gas, such that most molecules don't make a collision. A few molecules make collisions, and some of them fragment. And you can see the different fragment parts here. This is loose in the adenine plus the hydrogen atom. This is only the adenine left, and these are the phosphate groups. You can see directly here that if you instead exchange the neon for sodium, you get an additional peak, and that is the double minus AMP. And that is actually so that you have the negative AMP ion coming in, and this captures an electron from the sodium. It becomes doubly negatively charged. Okay.
So what was the significance of the neon? What happened with the neon? Momentum transfer?
In the case of the neon, you just transfer energy without transferring charge.
Right, yes.
And therefore the molecule breaks apart.
Yes.
And that's called collisional-induced dissociation.
Yes.
So the difference here is that in that case we have only collisional-induced dissociation. And in this case we have electron capture and, of course, collision-induced dissociation. You can't avoid that. You knock on the nuclei of the system. Okay, so this is the first now main result. Now we collide this molecule here, but we dress it with water molecules, a number of N water molecules. And we collide with neon, such that we only have collision-induced dissociation. And this is starting by 0 water molecules on it, and that's the spectrum we have just seen. Now, if we dress it with 5 water molecules, you see that you start to get, this is now the primary beam here, I should say, the outermost one. And then in steps, you see, here you have lost 1 of the water, so you have 4 left, you have lost 2, 3, 4, and this is losing all 5. Okay, so you see that the intensity goes down like this, and then it rises again when you reach the naked number. And then you see some fragmentation. Okay, and then we take 10 instead. And of course you have peak further out here on the scale. This is the primary peak then, and this is the different signals for losing 1 through 10 of these 10 water molecules.
Do you know why it goes up so much at 10? Is that
Well, that's because, I mean, that's 10 here, that's the primary beam.
not that one, but
This one. Yeah, I mean, this is basically because it's quite easy to get rid of 1 water molecule, but it's much harder to fragment the AMP itself. So sort of you can think of it that you have the intensity going down through the system and you evaporate the water molecules, and then it stops. The fragmentation because it becomes harder for the next step to fragment the molecule itself.
So this is a horizontal axis, your your M over Q, or what is it?
Sorry, yes, this is M over Q again.
And what does it mean, 400? I mean, what units and stuff? What do you think of this?
This is atomic mass units per charge.
Okay.
So the weight of the AMP molecule
Means
should
400
say, please remind me.
pieces, yeah?
370.
Yeah, I see. Interesting. Yes, yes.
Yeah, you can see it here.
Mm-hmm.
Okay, then when we take 13, okay, the same story again, and one can notice now that some of these peaks are disappearing. And if we take 20, which is the maximum we can reach, there's hardly nothing here. So already from looking at this picture and this development of the fragmentation pattern, we can say that having 13 water molecules or more, it protects the AMP from fragmentation under these
The
experimental.
AMP signal so weak.
Pardon?
But the AMP signal is weak.
Here,
Yeah.
because the primary beam is rather weak in this case.
Ah.
Yeah. So you can see here that the statistical quality is less than, for
Yeah, but
instance,
if you renormalize to the size of the AMP minus peak, doesn't it keep the same structure of these little wiggles?
well, the little wiggles, yes, the structures are preserved to some extent, but also there is a statistical limitation, because there are, of course, depending on the binding energies for the individual water molecules in different shells, you have some shell structures which we will see later. Right here, for instance. So this is now the same data, but in another representation. So we are again looking at the system here, the M water molecules to start with. We collide with neon, and we look for the distribution of intensities in the peaks, keeping different numbers of N molecules, where N is smaller than M. So if you look for 20 here, you see this distribution like this here, and then it goes up here, which is for the intact molecule, and then we have made sort of a point here for where we have summed the intensity in all these different fragmentation channels, where the AMP goes into pieces. Okay, so you can see here the progression if you take different numbers here. And you have some kind of features which are repeated here, like for 5 molecules there seems to be something special going on. Okay, so a simple model, a very simple model has been developed in order to look at this data here now for this part, where we look at the collisional induced dissociation. And then we have assumed that we have this kind of Arrhenius expression with some pre-exponential factor and some binding energy for the water molecule number I, and with some energy for the system before this step, when it loses molecule number I. Assuming that we evaporate them stepwise now. And this is what we assume to be known, and this is what we are going to guess. So we're going to guess this distribution then in order to find agreement with the experimental results. So then we have this system of normal coupled differential equations describing the time development of the intensity in the different peaks with different numbers of waters. Remember now that we look at the data after 5 to 10 microseconds. So this is not what will happen, if you wait to infinity, but this is what happens after 5 to 10 microseconds.
And the T is, which ballpark is that normally for these beams? Is that near the temperature?
The temperature, guessing a few thousand kelvins or so.
Okay.
Okay, so these are the model parameters used here, and we have them from literature. This value, which is 0.43 eV for the sort of the outer shell from the water molecules, and the water molecules are, according to some fairly simple calculations, then surrounding this phosphate group. For the first 5 molecules, the binding energy is stronger, it's 0.60, and therefore this small peak in the data. And the lowest dissociation energy for the AMP molecule itself is 1.26 eV. And this is the reason why sort of you get extra intensity in that. So these are typical shapes of these systems. And these are now the model results, and you can see that they agree quite well with the measurements. And it's actually quite sensitive to the assumed energy distribution of what you put into the system. We don't know this, of course, because the ion, the AMP minus with water on it collides with the target at different distances. Depending on this distance, it will transfer different amounts of energy. So there's a distribution of energies that goes into these equations. And the distributions that gave the best fit are the ones shown here, which has a funny unit on the scale here. This is in units of the 0.43 eV, which was the typical energy needed to remove one of the water molecules. And these are the results from the distributions for 6, 10, 20 water molecules. Okay.
So the background of this model, you will say a bit more about this, or
No.
I mean how good this is
Not really.
otherwise? Is this purpose-made, this model, or?
Well, this model,
Maybe it was a previous
it's not so
equation again.
important actually. I mean, the important
Yeah.
thing is the direct observation. And what I will use it for is to show that we can get, by this, it's extremely simple. It's only assuming that you have some activation energy and some temperature. And this is essentially what we fit here.
All the gammas, right, all the news.
Yeah.
But the news are different, no? Are they different for different
No,
times?
they are assumed to be the same.
And that was interesting, I guess.
Assumed to be the same. 10 to the 13 or so per second.
Yes.
Yeah. So it's a very simple model, but actually the result and the comparison is quite sensitive to what we assume in these distributions. And the reason why I say this is that I will use it for the next part of the talk, concerning the capture. Okay, so these are the results, like this, and this is just plotted in another way, showing again, this is now just the relative ion yields directly in the experiment. How much do we lose from losing water molecules? And how much do we lose from fragmenting in different parts of this AMP molecule? And this is now the total fragmentation of the AMP. And the important thing is that it goes down drastically here, as we saw directly in the data, when you reach something like 30 molecules.
That's because your radiation damage the collision with neon.
Yes?
So your radiation is sort of neon nuclei.
Yeah. That's right, exactly.
Nuclei.
Exactly, that's the radiation, yes. So from our point of view, it doesn't matter so much. You charge some energy into the system, and how does it break apart? And it's not so, actually we got the first referee report on that paper. They asked what is the biological significance of neon. But it's not important. Okay, so now, if we now return to this spectrum, I showed it once before, but again here, if we collide now the naked AMP minus no water molecules attached with sodium Sodium has a much smaller ionization potential than neon, and therefore it's easy to pick electrons. Okay, and what I showed before, what in the case of sodium, we get this AMP2 minus. All right, so sort of what we concluded, as I said already from the first experiment, was that the water had a very strong protective effect, and we don't need so many water molecules to protect the AMP molecule. But now if we look at the di-ion formation, double minus, and we start to dress the AP minus with additional water molecules. Here we have 4 water molecules. Here we have 30 water molecules. And what you see are distributions like this, which are different from the ones which we got from the pure collision-induced dissociation, in which we always had sort of a declining distribution like this. But here, for the capture case, we have sort of a local maximum in the middle of the distribution. So that's different. Furthermore, if one makes a careful scan here and a precise calibration, one can see that in all these cases, one loses an H atom from this system. So it's not really like I've written here. It doesn't keep the full system. It loses one H atom always. Now one should see what's the importance of this. Well, we can compare directly in this figure here. With 30 waters, you have the fragmentation from the collision-induced part here, and you have this for the capture part here. So this is blown up. So, I mean, the total cross-section from that process is much smaller than for this process. Still, I mean, it might be, because it always loses an H atom, that might be important. Okay, here's another example. This is now with 16 water molecules attached. And you can again see this peak distribution here. And it's such that with 16 molecules to start with, you don't find much intensity where you have lost only 1 or 2, 3. That's 0. So that's an important factor. But then you have all the peaks going down to 0 waters left.
And you feel sufficiently confident in the calibration of the mass scale so that you know that it's 1 H atom?
Yes. I mean, that's I should say, still somewhat preliminary, but I mean, we have made, in some of the cases, we have checked that, and this seems to be the case.
Just running with heavy water would be a simple check to see that it shrinks.
Yeah.
So sorry, coming back to the referee's question, why does this distribution not depend on your probing, on your radiation actually?
Well,
That would take something else.
it has to do with, I mean, now we changed the target from neon to sodium. That's about the same mass. It doesn't, I mean, it's not a big difference. But as I said, I mean, the difference is that you transfer the electron. And by the electron transfer process itself, you deposit probably some energy into this distribution.
But wouldn't that look very different from typical radiation, which I would expect in biology?
That could be. I mean, but I mean, this is a way to put a certain amount of energy into the system. And what way? I mean, if that's excited in some other way, maybe that doesn't matter so much, as long as you have the same charge on the final system. So we look at it as a way to get energy into it.
Do you know where the charge ends up in the system?
That has been a little bit discussed. That we are not quite sure about that. So.
In the wall, one would think, maybe in the end. No?
What do you say?
On the wall, in the end.
On the wall, yes.
Yeah, no?
Yes, but before then.
Yeah.
Between the beginning and the end.
Okay.
Yeah.
Okay. Now here are some, we have to say, preliminary results of the distributions for different numbers of kept electrons in the case that we have also electron capture. Remember the distributions I showed some time ago? They looked like this, also with a logarithmic scale, so they go up very strongly when you lose few water molecules. But in this case, it's just the other way around, that you don't have any intensity when you lose two molecules. Somehow, this process where you capture an electron, it must transfer sufficient amounts of energy to always spit out at least a few water molecules. So what we try to do now is that we use that same simple model which I showed you before, this evaporation model. And then we look for the distribution needed in order to reproduce the results. And it looks like this. Instead of having just a cutoff and an exponential part, it has a maximum. And it's quite sensitive, and the person who did this, it's not me, I didn't do it, but one of our colleagues, and he claims that it's really impossible to get any agreement with the experimental results without this maximum. And somehow I believe that this is related to the fact that you capture an electron, that this is a selective part of that process, that somehow you enter a certain impact parameter interval or something like that. But okay, I mean, this is just a model, and that's not the important part here. This is just a way to roughly understand what's happening in simple terms. And also, finally, I should say that since we believe that we always lose a hydrogen atom here in this capture process, it's important to see if we now make more and more water molecules on this biomolecule, what happens to the cross-section? Well, it's not so surprising perhaps, but the more waters you put on it, the larger the cross-section. So if you say that, okay, in the first part of the experiment, we showed that putting water on is protective. Okay, we protect it, doesn't break apart. On the other hand, if we also capture an electron, the more waters we put on it, the more we break it apart. Because the cross-section is larger for breaking this hydrogen away from the molecule.
Do you know where the hydrogen comes from?
It is believed that it comes from this part of the molecule. This one, which makes the hydrogen bond in the base pair. But this is not for certain. I mean, this is a speculation. But if so, that might be an important result. If it's harmful in such a way that it harms the functionality of the molecule, maybe it's important. But I think somebody said to me, who knows better than me about these biological aspects, is that this is easily repaired. It's easy to find another hydrogen atom to bind with in the real situation.
But I thought repairing only works among living DNA. Isn't that right?
But
the regular normal repair, DNA repair. If it's dead, nothing repairs it.
But this is more like on a molecular level.
Something
I mean,
different, I
if
guess.
it's
I don't know. Definitely repairs in living.
Yeah.
okay, but I mean, we are not sure about this if it's that hydrogen molecule. But I mean, it's speculated that it might be. Okay, so I would conclude then by saying that, I mean, the important part here are the experimental results, and we have seen that 13 attached water molecules protects the AMP from collision and induced dissociation. On the other hand, the electron transfer process appears to be more and more harmful the more water you put on it, because the cross-section for taking the hydrogen off is becoming larger. It thus appears that few solvent molecules really can protect biomolecules from damage, at least from the point of view that the cross-section for this protected part is so much bigger than from the harmful one. In single interactions, these were interactions with just one target molecule. However, if you imagine that you shoot biomolecules through an atmosphere, you will make many collisions. And of course, if you remove waters in sequential collisions, you can remove many of them. And I think this is an experiment that Henrik will do in the basement of the Nancy laboratory. Then you will have to put many waters on.
So 13, does this mean that this is the closing the first formation shell, or?
No, that's 5 water molecules. So this is, yes, second shell.
Second.
Yeah.
But the formation shell is not the entire molecule.
No. It's like here. I mean, that's also an interesting aspect, that the molecules are not surrounding the whole biomolecule, but it sits on this part, at least according to some calculations. And therefore, I mean, the way it protects is that when you dump energy into the system, it cools down by emitting these loosely bound water molecules. It's not that they physically protect this one from being hit. So, of course, if you put very many waters on it, then at some point it will surround it. Okay, so this morning we had some forskningspresentation for the students on the third year. And then I made an overhead of the people which I work together with mostly. And this is Peter Henning, you know, and Zoltan Berni is now into private business in Hungary. He's retired here. Daniel Fischer never provided a photo during 2 years. Dipanka just came from India as a postdoc. Myself, Magnus, he's here also. And Nicole, and you know this guy, I think. And Henning Zettergren, he's now into some second league team in Aarhus. But we will get him back at some point. We have people working specifically with Desiree, Stefan Lucen, and the tech expert, Richard Thomas, and Wolf, you certainly know. But, I mean, they don't work full-time, all of them, for the Desiree project, but we have others tasks as well. And this is not quite right, I know, because Richard is not free electron laser paid, but he works on that project, and I couldn't resist to put this label on him after. The collaborations we have are mainly within its late network, which runs until 2010. And some of the people here are coming through that network, and the collaboration which I have been discussing results from is also within that network. And these are the people who participated in this experiment. It's people from here, and it's people from Aarhus, which involves these two guys, Preben Weltland and Sten Nielsen, and Henning Zettergren, who is now postdoc in Aarhus. And two people from Janil, Bernd Huber, and Bruno Manil, who made these calculations. And this is Bo Liu, and he's the one who sort of got the idea with this hydrogen loss in the capture process. And he comes here on Tuesday to work on this project. He's now in China. He's been a postdoc in Aarhus before. Okay, so that was the end, and thank you very much.
Thank you, Henrik, for a very clear presentation. Question, please. So, when you say hydrogen loss, and you mentioned also electron gain, is that sort of equivalent? Are you talking about the same thing then?
No, not really. I mean, electron transfer. So,
yes.
Yes. So the electron transfer process is, of course, I mean, you transfer an electron from the target and you make the sodium plus, and this electron goes somewhere in the system and forms some excited intermediate system which has some energy in it.
Yeah.
And this energy, I think we get a clue on that through this simple model, that we have the approximate distribution. And of course we can see there how much, I mean, this is of the order of a few eV that we get into the system.
Do you know if this dianion is stable?
Yeah, I think the ground state is stable. But also, according to expertise in Aarhus, it's not the ground state which is excited, but it's excited states, or which is populated excited states. Mostly.
Just remind me, there was no hydrogen loss with the nation.
Right. That's correct.
How long time do you run an experiment if you have
the tricky part is to make this beam. And but once we have the beam, it's a matter of a few hours running time. So it's rather short experiments. But the tricky part is to get this beam. And actually for this specific experiment we have managed to make the beam a few times, but we have also failed many times. Like, for instance, last week I was there and wanted to make some additional experiments that didn't work. And it's some, I mean, now chemistry is involved here, so that becomes complicated. So the exact composition of the solution in this spray is important. They have lots of tricks to add some salt or something like that also to improve things.
These fragments, I mean, when you fragment it, what did the fragments look like? Did you show that?
Yes, it's, you can see, here's typical,
Yeah.
you get peaks from important parts of the molecule, so to speak. Here, for instance, you have lost one adenine and one hydrogen atom in this case. And here is only the, well, that's the adenine itself. Of course, the other part here is neutral, then, so you can see it.
What about the sugar? Where is it? Is the sugar totally smashed up? Because you never saw the sugar in these diagrams. So
Yeah, that's indeed a related question.
Yeah, maybe, well, wait a minute, what's the...
You may not be able to see. I mean, the only way to see this is if you actually have oscillations from any particular bindings. But maybe none of those in the sugar will actually produce any.
Well, since that we didn't, I don't have labels or not, let's see, what's the mass of that? Somebody... it might actually be some of these other things here.
But I mean, do you after that just find some clean cut of the phosphate, the sugar, and the adenine, or is the sugar totally smashed up? Do you have some sugar and phosphate and sugar and adenine, or
maybe it's neutral because then you don't see it also. I don't know.
oh yes, that's always the problem.
Yeah.
Oh yeah.
So probably that's the case because it's in the middle.
Yeah, yeah,
You see the charge factor.
Yeah.
Have there been some similar experiments for radiolysis or photolysis of this? You can compare the effective effect.
Not as far as I know, but that doesn't mean that there hasn't been any experiments. I don't know.
I mean, you've got a lot of phosphate, phosphoric acid,
Yeah.
but you don't have very much of what was over. That is the A minus, which is left when you've taken away the phosphate.
Mm. But that, again,
Doesn't look like a mass balance.
no, but you have to remember also that you have to have them charged in order to see them.
Yeah, yes.
Yeah.
So I'll ask some stupid biologist questions. So is it just because of this issue with charge that you're focusing on this hydrogen
Yeah.
loss and not other types of damage? So you're limited at what you can study because of this setup, or? For a biologist, for example,
Yeah.
that wouldn't be the most likely type of damage we would maybe be worried about seeing in, say, biomolecules
Mhm.
from. Say if we found molecules on Mars, we wouldn't be probably looking for that type of damage. So
Okay.
I'm just wondering.
Yeah. No, I mean it's sort of limited to what we can see with different, reaction channels in this case.
Okay. So then, with respect to this protective effect with water, and these two questions of what was the biological significance and what's the astrobiological significance, have you got any take-home message on that in terms of, say, molecules of possible biological origin elsewhere and protective effect of water or other such things?
Not more than to say that, obviously if you attach some water or any other solvent molecules, you do protect it, because there's another way to get rid of excess energy for the system. So if you want to protect the molecule itself, you can, if you dress it with for instance, water.
Okay. So how much damage do you think, are there real environments out in space where this type of damage might really occur and affect biomolecules in this way?
Well, in the case that you had, sort of ion collisions in some regions in space, this certainly must have be relevant process.
So you mentioned atmosphere re-entry. Is that unlikely?
Yeah, I mean, I would say right away that, I mean, if with only 20 water molecules on, I mean, you get rid of those immediately, I mean, when you make a few collisions.
Okay.
But I guess the idea here is that you have very many, I mean, microscopic amounts of water molecules around biomolecules if you want to have them sort of to the face of the Earth.
Okay.
I don't know, of course. So.
But you don't see any positively charged fragments then?
Well, you can if you change the polarity of it. Yeah.
But did you look for it?
Not in this case, we didn't look for it, but in other cases we actually did. So we have been doing a range of experiments. I mean, Nicole and Henrik were in Norris last week, and they made some experiments with dipeptides, different numbers of waters, and other solvents as well, I think. Yeah.
You can't look at neutrals.
Neutrals, no, it's hard to determine the mass. Of course,
you use the multiple moment and stuff like that.
That is in principle possible, yes, but it requires very high fields. For these energies, we have 50 kV fields. But there are storage rings for neutral molecules, for instance.
And in practice, how do you actually steer the amount of water that you have there? How do you change that? Do you just have a temporarily measure, of course, afterwards how much you got?
Yeah, I mean it's simply done by select. I mean, we get the distribution of it, and then we select one of them, and it's a matter of getting enough intensity.
Yes.
And the resolution is enough to select?
Yes. Yes. This is a huge magnet. What's the radius? I think 2 meters. 2 meters.
And this is a machine in orbit.
Yes. It's a principle 50-year-old technology exactly at this point.
So just a question about this very early slide you showed where you had the deuterium replacement to try and establish which hydrogen was coming off.
Yeah.
Does that allow you to fiddle around with, I guess you can look at different, if you protect, you can look at different hydrogens and see if you can see a difference. Is that something you're planning to do?
Well, maybe, but I mean, we don't have any specific
Reason?
specific plans at the moment, but I mean, that could in principle be possible.
I'm just wondering whether you can, one can pick
Can-
up weak spots in the molecule.
You mean to protect this one from breaking, for instance?
Yeah, I guess, are you concluding here that NH is the weakest one that's going first?
Yeah.
But then if you protect that, you could look at the other ones as well, I guess.
Yeah, right, exactly.
Great. So that was very interesting to hear about these interesting aspects. Okay, well, thank you.
Yeah.